Welcome back to the deep dive. Look, if you live anywhere that experiences unpredictable weather, you've probably noticed something. Well, unsettling. Power outages seem to be happening more often, and they last longer.
Yeah, it feels that way, between the storms and grid issues.
Exactly. And reliable backup power isn't just nice to have anymore. It's becoming an absolute necessity for a lot of folks. And when we talk backup power, the gold standard is still the generator.
Right.
But the market's changed quite a bit, which is why we're here today. Our mission, cut through the confusion. We're doing a deep dive into the two main types, the traditional conventional generator, you see those everywhere, and the newer, more sophisticated inverter model. So you can walk away knowing exactly which one fits your needs for, say, 2025.
And the core thing we're looking at today, it's really interesting. It boils down to two totally different approaches. Do you want just sheer raw power, brute force energy? Or do you need clean, stable, efficient power?
Mm-hmm.
We really have to get into the fundamentals, the mechanics, because that difference, that's what determines if your expensive laptop, makes it through the next blackout.
Okay, right. Let's unpack that. Starting really basic, both types, whatever they look like outside, do the same core job. Take fuel.
Gasoline, propane, diesel.
Right, and turn that chemical energy into electrical power. There's an engine inside doing that work. But the moment that power is actually generated, that's where they split onto completely different paths.
That's the perfect way to frame it. So let's look at the workhorse first, the conventional generator. This is the simpler machine, really. It takes the fuel, converts it directly into alternating current AC. That's the power from your wall socket.
Right.
It uses an engine alternator for this.
Okay, direct conversion.
Direct conversion. But here's the catch. To produce the 60 hertz frequency that, all our standard appliances in North America need, that conventional engine, it can't vary its speed. It has to run at one constant maximum speed, usually 3,600 RPM, nonstop.
Like a car stuck in high gear.
Exactly.
Yeah.
Think of it like that. Stuck in fourth gear. Doesn't matter if you're climbing a hill or just sitting there idling. It's always revving high.
So if it's always at max speed, what happens to the actual electricity if I, say, turn on a big appliance or turn one off? Check the load.
Yeah, the output gets, volatile is the word. That constant speed doesn't react smoothly to demand. You flip on something heavy, the engine bogs down for a second, voltage dips. You turn something off, suddenly voltage spikes up. That instability is just baked into the design. It prioritizes constant mechanical speed over refined electrical output.
Okay, so that's the conventional. Now let's talk about the inverter. The game changer, as people call it. They also start by generating that raw AC power, right? But then there's this extra step.
Yeah, a crucial intermediary step is more like a three-stage dance. Stage 1, generate the raw AC, just like the conventional. Stage 2, immediately convert that messy AC into direct current, DC. Think like battery power. Uses something called a rectifier.
Okay, AC to DC.
Then stage 3, this is where the name comes from. They use sophisticated microprocessors to invert that smooth DC back into perfectly stable, clean AC power.
So that whole inversion process, it's like a purification system, a stabilizer.
Exactly. It cleans and stabilizes the power. And here's the key benefit of that process. Because the microprocessors are managing the final AC output frequency, the engine itself, it doesn't need to run at that constant 3,600 RPM anymore. The engine can actually throttle its speed up or down based on the actual electrical load you're asking for.
So if I'm just running a single lamp,
The engine just idles along, nice and quiet.
but if I start the fridge,
It speeds up just enough to meet that demand. No more, no less.
which means, okay, it's got to be way more efficient and quieter. But let's talk about the really critical thing for anyone with, modern electronics, power quality. I keep seeing this term, THD, total harmonic distortion.
Yes, THD. And this is where that design difference precision versus raw power really becomes fascinating and, frankly, critical.
Yeah.
What are you actually trying to power? THD is basically a measure of how clean or smooth the electrical waveform is. Think of it like ripples on water.
Yep.
High THD means a choppy, messy, distorted wave. Low THD means a smooth, pure sine wave, like what the utility company delivers, ideally.
And you mentioned conventional generators produce dirty power.
Yep.
That sounds kind of scary. If I plug my expensive laptop into that conventional generator with its, up to 25% THD, am I really risking frying it?
It is a genuine risk. Absolutely. That's why we're digging into this. Your sensitive electronics laptops, smartphones, smart TVs, medical devices, anything with a microprocessor. They rely on that smooth power delivery. Hit them with 25% THD. You run a real risk of damaging components, corrupting data, or sometimes the device just shuts itself down to protect itself. which isn't helpful in an outage. Now, inverter generators, because of that whole AC-DC AC conversion and the microprocessors, they produce what's called utility grade or clean power. Their THD is typically under 5%, sometimes even lower, under 3%.
Wow, that's a huge difference.
Massive.
Yeah.
That stability means the power is perfectly safe for pretty much any electronic device you own. Well, it's the peace of mind you're paying extra for, essentially.
Okay, that makes the choice pretty clear if you, say, work from home or have sensitive medical gear. But beyond just protecting your stuff, let's talk about the experience, the quality of life stuff, noise and runtime before we even get to decibels. That noise factor. I remember trying to sleep near a neighbor's conventional generator during an ice storm once. Felt like a jet engine was parked next door.
That's not far off. That constant 3,600 RPM means they're just plain loud.
Yeah.
No way around it. We're talking 70 to 90 decibels. And to give you some context, 70 dB is like a vacuum cleaner running constantly. 90 dB, that's a lawnmower right outside your window all night.
Yeah, okay, so if your neighbor has one, you will know about it.
You will definitely know. Now, compare that to the inverters. Because that engine throttles down under light load, they're often described as whisper quiet. Typically in the 50 to 60 decibel range. That's more like a normal conversation level or maybe the hum of a refrigerator.
Big difference, especially if you need to run it for days.
Huge difference. And that variable speed directly impacts runtime and efficiency too, right?
Yeah.
If the engine isn't screaming at full speed all the time.
It's sipping fuel instead of guzzling it. Makes sense.
Precisely. That variable speed makes inverters somewhere between 20 to 60% more fuel efficient than the conventional model of the same approximate output.
60%, wow.
It can be significant, especially under partial load. So a conventional generator might give you, 4 to 8 hours on a tank of gas, if you're lucky. Many inverters, even smaller ones, can easily push 8, 10, even 12 hours on a pretty small fuel tank. That's huge in a multi-day outage when fuel might be hard to find.
Okay, so inverters are clean, quiet, efficient. But here's where it gets tricky, right? The trade-offs. Cost versus actual power output. We know inverters usually sacrifice that massive power output for all the sophistication.
That's generally true. Conventional generators.
Yeah.
They are still the undisputed champs of just raw brute force power. If you need to power a whole construction site, run your entire house, including the central air conditioning, maybe start up a big well pump, you need the kind of massive wattage a conventional generator provides. They range from, say, 5,000 watts up to 20,000 watts or even more for the big standby unit.
And they're built for that kind of heavy work. They're usually pretty bulky, right? Big metal frames, heavy.
Oh, yeah. Often 100, 200, sometimes over 300 pounds. They aren't really designed to be moved around much. You kind of set them up where they need to be.
Right.
And they naturally have something critical for those big loads. Really good surge capacity.
Surge capacity. Explain that.
Okay, so when a big motor starts up, like in your refrigerator, air conditioner, or well pump, it needs a huge but very brief burst of extra power just to get going. That's the surge. Because a conventional generator's engine is already spinning at that high 3,600 RPM, it inherently has the momentum and grunt to handle those sudden big power demands without stalling.
Gotcha. And inverters being smaller.
Yeah.
Maybe not so much surge.
They typically have less surge capacity, watt for watt, and their overall power output is lower. As you said, you usually see them in the 1,000 to maybe 7,000 watt range, much more geared towards portability.
Yeah, that's a key feature, the portability.
Absolutely. They're often much lighter, maybe 40 to 100 pounds, compact, easy to carry, easy to store, perfect for camping, tailgating, RVs.
Okay.
But while their individual output is lower, they have a really neat trick: flexibility. Most modern inverters are parallel capable.
Meaning you can link them together.
Exactly. You can buy two smaller, identical inverter units, say 2,000 watt models, and connect them with a special simple cable. And boom, you've got 4,000 watts of clean power available when you need the extra capacity.
Ah, that's clever. So you get scalability.
You get scalability and you keep the portability because you're only moving one small unit at a time. It's a huge advantage.
Okay, let's hit the bottom line then. The thing that often stops people, the cost. Inverters are known for having a significantly higher price tag up front, sometimes like 50% more than a conventional generator with similar wattage. Why spend that extra cash, especially if you only expect to use it, say, once a year for a big storm? Does that $200 a year fuel saving really matter then?
That is a perfectly valid question, especially if your main focus is just the initial purchase price. Conventional models, $300 to maybe $1,500 for a decent-sized one, they definitely look like the budget-friendly choice up front.
Right.
However, The return on investment, the ROI calculation for the inverter. It can change the math pretty quickly, even if you only use it occasionally. You're essentially for three things up front with that inverter premium: the sophisticated electronics for clean power, the much better fuel efficiency, and frankly, the protection for your expensive devices. The sources we looked at suggest that because they burn so much less fuel, that 20-60% figure, you could potentially recoup that initial price difference in fuel savings alone within just 1 or 2 years, if you use it regularly or heavily.
Okay, for heavy use, I see it, but what about occasional use?
Even for occasional use, over the typical lifespan of a generator, say 5-10 years, those fuel savings add up. Plus, you have the quiet operation, the clean power protecting your gear. It becomes a value proposition, not just a cost.
So maybe a rule of thumb is, if you're a light to medium user, you need that clean power for tech, and you'll use it somewhat regularly. The inverter is probably the better long-term investment.
I think that's fair.
But if you just need maximum power for one massive event a year and initial cost is paramount, the conventional still has that edge.
Precisely. And that leads right into thinking about the application. The choice really has to be guided by what you're going to use it for and where, not just the price tag.
Okay, so give us the breakdown. Ideal use cases for 2025, thinking about how we live now.
All right. Inverters are really perfect for modern life. Recreational use, shore camping, tailgating, but increasingly vital for home emergencies where you need to keep your tech running. Think running lights, your internet modem and router, charging phones, keeping a laptop going for remote work during an outage. The quiet, clean inverter is hands down the winner there.
Yeah, remote work makes that critical now.
Absolutely. And also great for small businesses, maybe food trucks or vendors who need quiet, temporary power without disturbing neighbors or customers.
Okay. And the conventional models, where do they still dominate?
They're still the workhorses for a reason. Construction sites, definitely. Large farms or agricultural operations needing serious power. Workshops with big tools. And that large-scale home backup scenario where raw power is just more important than noise or peak efficiency. Yeah. If your main goal is running multiple air conditioners, a big well pump, and your deep freezer simultaneously, you probably still need the grunt of a big conventional generator.
Right. The power plant model.
Exactly.
We should probably also touch on some of the evolving standards for 2025. Thinking about emissions and maintenance, these definitely factor into the long-term ownership picture.
Good point. Emissions are becoming a much bigger deal. Inverters naturally tend to have lower emissions because they're more fuel efficient, throttling down that engine. Makes it easier for them to meet strict standards like CARB in California.
Okay.
But the conventional generator manufacturers aren't standing still. We're seeing a huge increase in dual fuel and even tri-fuel options over there.
Running on gasoline, propane, and natural gas.
Yep. Letting you choose cleaner burning fuels like propane or NG helps reduce that environmental footprint and adds a lot of flexibility, especially if one fuel type becomes hard to get during an emergency.
Smart. And what about maintenance? Based on how they work, seems like there'd be trade-offs there too.
There are. Conventional models running flat out at 3,600 RPM all the time. They generally need more frequent basic mechanical upkeep, like oil changes, spark plugs, air filters, standard small engine stuff.
Okay, more routine work.
More routine work. Inverters, on the other hand, their engines often experience less wear because they run slower much of the time, so maybe less frequent oil changes. But
there's always a but.
There's always a but. They have those sophisticated electronic components, the rectifier, the inverter module itself. If one of those fails, that's not usually a simple DIY fix or a quick trip to the local mechanic. It can mean a more expensive, specialized repair.
Ah, okay. Simpler mechanics versus complex electronics. Trade-offs again.
Always trade-offs.
Let's try to make this concrete for people listening. Can we give maybe 2 specific examples that really highlight this divide? Like one top pick for inverter, one for conventional.
Sure. For the high-end inverter market, a classic example our sources often point to is something like the Honda EU2200i.
Heard of that one? Very popular.
Super popular for a reason. It's incredibly quiet, like 48 to 57 decibels, really lightweight, about 47 pounds, gives you 2,200 watts of very clean power, perfect for camping, tailgating, or basic home backup for essentials and tech. You're looking at around $1,100, maybe a bit more.
Okay, premium price, premium features.
Exactly. Then for the brute force conventional side, you might look at something like, say, a Generac GP9500E or similar. This thing's an absolute beast. Puts out 9,500 running watts, often available in dual or tri-fuel. It's built for serious work, whole home backup potential for many people.
And the price?
Interestingly, often priced pretty similarly to that high-end Honda, maybe around $1,000 or $1,200 depending on features. but you're getting over 4 times the raw power output. Just remember, it'll be much louder and less fuel efficient.
Huge difference in capability for similar money, but totally different use cases.
Totally different. And no matter which way you lean, please calculate your actual wattage needs first. Add up everything you absolutely need to run. And always prioritize safety features, especially carbon monoxide detectors. They're crucial.
Absolutely critical advice. Okay, so wrapping this up, what does this all mean when you're standing there looking at these two very different machines? It feels like the decision really boils down to your main priority, doesn't it? Are you prioritizing efficiency, quiet operation, and safety for your modern, expensive tech?
If yes, then the inverter is almost certainly your choice.
Or are you prioritizing raw surge power, the absolute maximum wattage output for heavy loads, and maybe the lowest possible initial purchase price?
Then the conventional workhorse still makes a very strong case.
So the takeaway for you, the listener, seems clear. Inverters are dominating for that modern tech-heavy lifestyle, for portability, and for better long-term running costs through fuel economy.
Right, but conventional models, they're still just unbeatable when the job demands serious, high-wattage, heavy-duty muscle. They have their place, absolutely.
Okay, final thought to leave everyone with. Given how popular inverters are becoming, and with all the talk about fuel costs and cleaner energy, how might these newer hybrid or maybe really advanced dual fuel models, the ones trying to blend that inverter efficiency with higher power output, how might they fundamentally change the game for home backup power over, say, the next decade?
That is something interesting to think about, bridging that gap.
Something to mull over as you're calculating those wattage needs.